Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to actually do a very weird and very cool, to show you a very weird and very cool pattern that relates eigenvalues to determinants, and also eigenvalues to the trace of a matrix, which again is that sum of the main diagonal. So, and I'm going to try to prove both of them, but they are pretty tough proofs, to be fair. And so they'll be a little bit hand-wavy, but at least kind of show you the idea behind both of these. So to get started, I just want to find determinants of a few matrices to kind of motivate this idea. So, like if I'm not going to go through every one by hand, but you should be able to do all of these by hand. The last one's probably the hardest one because it's got no non-zero entries, but, ones like, this one I would expand along this column. For this one, I'd expand along that column. The top one, maybe I'd expand along the bottom row. Maybe I can kind of do some of the first one right here. So for the determinant of A, if you do the pattern plus, minus, plus, minus, plus, minus, and then plus, minus, plus again, you would have 0 times something, so we can just ignore that. The negative 1 times the determinant of 1, 0, negative 1, 1, and then plus 1 times the determinant of 1, 2, negative 1, negative 1. And so this would be negative 1 minus 0, and then we'll do plus negative 1 minus a negative 2, so plus 2, which is 0. So you should go through and be able to do all those. If you do those out, so I'm going to use them actually over here. You should see that the determinant of this one is 0. This one is negative 6. This one is 27. And this one is negative 90. And just to speed things up, down here, you could do this with using your calculator or something. You could just do eigenval of all these. But the eigenvalues of A are 0. Eigenvalues of B are 1, negative 2, and 3. For C, it's 3, but it has multiplicity 3, algebraic multiplicity 3. And for the last one, it's 3, negative 5, and 6. And so at this point, so again, this one was negative 90. If I was you, I would pause the video and see if you can kind of make a hypothesis as to some sort of connection between the determinants of these matrices and their eigenvalues. And 0 is kind of a weird thing. And actually the first one, 0 has algebraic multiplicity 2, but then you have 1 as an eigenvalue also. And that's going to actually kind of be important to help you figure out the answer to what I'm getting at here. So it may be easier to use some of these other cases with the determinants. But I think I've given you enough time to pause the video. Hopefully what you kind of saw is that there's like a multiplication going on. So it sort of looks like the determinant of a matrix A is equal to the product of its eigenvalues. And that turns out to be probably the worst question mark that the world has ever seen, but it's right there. And turns out that is actually true. And it's really weird. And when I saw that, I didn't believe it. So there's got to be some sort of geometric connection then between, these things. This is this measurement of how much the scale factor in the transformation changes, right? So like if you have a determinant of 1, then the matrix is not like, if you take a random little patch of, space, it's not warping that space at all. It's just keeping it the same. But if you have a determinant of 2, then, if you have a unit square of space, then it scales it by 2, and now that's a unit, it's 2 by 2, right, instead of 1 by 1. And so it's saying if you multiply all the eigenvalues, then it's equal to that determinant, which is really weird. So I want to prove that, okay? And that's what we're going to do right here. So basically we have like a complete set of eigenvalues, lambda 1 through n, for some n by n matrix. And we're going to prove that the determinant of A is equal to a product of those. And there's a few ways to do this, but the easier way to do this is actually, I'm going to kind of give you a curveball here and going to give you actually a different definition. So, so the actual definition of the characteristic polynomial is the determinant of lambda I minus A. And I don't really want to get into why it is different. What we actually do when we use this part, right, in computations is we set the determinant equals 0 and we find the roots. And basically what this is, right, is the, before we did A minus lambda I, so there's like a negative introduced here. And the way I think about this, why it doesn't really matter, is like if you have x squared, let's say minus 1, set equals 0, versus negative x squared plus 1 equals 0. X squared minus 1 looks like that. And the roots are still 1 and negative 1. Negative x squared plus 1, right? If we introduce a negative, it doesn't change the roots. And so it really doesn't matter if you're doing a positive or a negative one here. Like the way, a lot of times you would teach an Algebra 2 student to solve this, so just multiply by a negative, you get this one, and then you just solve this. But like maybe this is truly the quadratic that popped up in their problem, but for the purposes of finding roots, which is what we do with this determinant thing, we set it equals 0 and solve for roots, we don't care, right? So computationally, our brains actually are used to just A minus lambda I, because it seems a little more, I think, natural to just do A minus that thing. But technically what would show up is actually this one. This is the true characteristic polynomial. So that's just like a weird little thing. But I won't use this one too often. I'll just still use the normal one that we're used to. But really doesn't change for purposes of finding roots, right? Because of this. Okay. So what we're basically doing with the characteristic polynomial is it's a polynomial, right, in lambda. So I can, lambda is just an arbitrary variable, all right? So I'm going to do, I'm going to evaluate what P of, I'm just going to let's start this way. So I'm going to let lambda equal 0, all right? And in P of lambda. And I can do that. It's just a polynomial, letting lambda equal 0 is fine. All this is basically going to do is it's going to simplify things for me. I'm not saying lambda equals 0 is an eigenvalue or something. Those are denoted by like lambda 1, lambda 2, lambda. Those are separate things right there. So if you let lambda equals 0 in P of lambda, okay, then basically you're going to get, P of 0, which is going to equal the determinant of 0i minus a, which, of course, would simplify to the determinant of minus a. Okay. And then I guess we could even go a little further here. So we know our eigenvalues are these values right here. So this means that P of lambda, right, would equal lambda minus lambda 1, lambda minus lambda 2, dot, 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 lambda minus lambda n, right? This is just algebra 2 stuff again. Like, these are the factors, right, that give me these roots. So likewise, P of 0 would equal, if you just pop a 0 in here, right, you can see that you'll get negative lambda 1 times negative lambda 2, dot, 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 times negative lambda n, which, you have n negative 1s. So I'm going to take that out, negative 1 to the n. And then I'll just have lambda 1, lambda 2, dot, 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 lambda n, like that. Okay? So that's just another fact about this characteristic polynomial, right? Okay. So at this point, I'm going to pull in a property of determinants. So we didn't prove this, but it's in the book, and it's a pretty straightforward proof. But we know that the determinant of k times a is k to the n determinant of a. And that's just a theorem from before. You can look at the video with the determinants. I brought that one up. Determinant of negative a should equal negative 1 to the n, because it's an n by n matrix, times the determinant of a. All right. So we're basically there. So up here, we had P of 0 is determinant of negative a. P of 0 is also this thing, right? So using those two above, we can just say note determinant of negative a would equal negative 1 times lambda 1, lambda 2, blah, 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 lambda n. Determinant of negative a also equals negative 1 to the n determinant of a. So, right, if we just equate the parts here, we have determinant of a and product of eigenvalues. I don't know, I'm finishing green. So, determinant of a truly does equal lambda 1, lambda 2, so on up to lambda n, which I think is a really weird, cool thing. Hopefully you do too. But yeah, if you think through this, I'm really not breaking any rules. Honestly, this part is a little weird maybe, but honestly, it's just, think about it this way. You either have an open up or an open down quadratic, but the roots are the same. And actually, truly, if you go and look at the definitions in kind of upper level linear algebra books, this is the one that they like to use. But typically it's easier computationally to just introduce a negative, flip things around. And then sometimes students don't like this step, but I'm not saying an eigenvalue is 0 or something. It's not true just for eigenvalues of 0 or something. I'm just saying if this is what the polynomial is, or, in general, this is what the polynomial is, then I can just, P of 0 here should be P of 0 here. That's all I'm saying. So this part equals this part. I'm basically just killing off all the first few terms of the polynomial and looking at the last term in the polynomial, right? And turns out that, determinant of a is the product of the eigenvalues. All right. So another result that is very weird, and I could also have you do this. So I could go back here, and with these eigenvalues, the trace of, take this one. The trace is the sum of the diagonal. So 1 minus 1 is 0, plus 1 is 1. And if you add up 0 plus 0 plus 1, it's 1, which is weird. The eigenvalues of this one are just the diagonal, which is the result of being upper triangular. But there, 1 minus 2 plus 3, if you add those up, right, it's the trace because that's the main diagonal. This one's a little more interesting. So 4 plus 3, 7, plus 2, 9, right? And if you do 3 plus 3 plus 3, it's 9. Negative 2 plus 1 plus 5 would really equal, the trace of that would equal the sum of these two. So very weird. And another thing that makes my brain hurt. Trace is something that you kind of study more of conceptually later on. And it has to do with, actually, I've seen it related to the derivative of stuff, and I'm a little bit fuzzy off the top of my head of how it relates, but it actually does also have a geometric meaning. And if you want to talk about that, we can do that. But right now, I just want to sort of argue why the trace of A is actually the sum of these eigenvalues. So let's do that. So this one is actually a little bit trickier than the previous proof, and the previous one's also kind of tricky. So this one I'm going to definitely do a little more hand waving, but I think it's good to at least show it. So at one point we had a problem where we had a characteristic polynomial for a quadratic, and I think this was in section 4.1, and we saw that lambda squared minus the trace of A times lambda plus the determinant of A was equal to the determinant of A minus lambda I. And so if you literally just go through a general ABCD matrix or something, we saw this pop up, and there was a problem that we worked through with that. And actually you can even think of, so that's for a 2x2 matrix, and you could even think of a 1x1 matrix and see it there too. So if you think of a 1x1 matrix, just literally A, and do A minus, lambda I, which is really just going to be A minus lambda times the number 1, right? You get a polynomial A minus lambda. Notice that this term is a negative polynomial. This one's a positive polynomial. You can kind of imagine that the sign will alternate based on how many terms you had, right? Because if you do another, if you multiply along the diagonal, A11 minus lambda, and then A22 minus lambda, and then A33 minus lambda, right? Now you're going to get you're going to be back to an odd polynomial. So you went odd first order polynomial, even second order polynomial, odd third order polynomial, and it really does just keep alternating. So one thing that I'm just trying to argue here is that for these characteristic polynomials, there's an alternating sign that happens with it, okay? And they always would have a lambda to the n to start you off. And actually, in the last problem, we saw that if you kill off all the lambda terms, you just plug in 0, your constant term at the end was the determinant. And that's actually true, that this polynomial would always end in determinant of A, with a negative 1 to the n stuck in front of it. And the weirdest part is that this trace thing that popped up in a 2x2 actually always also stays there. So if you do, and this is the part that I'm not going to kind of get into a ton, but if you actually compute it out and kind of start trying to sell yourself on this, the n minus 1 term, which for a second order, right, is just lambda, the n minus 1 term will always have a trace of A as the coefficient. It's pretty weird, and you should check it out. If you do out of 3x3, you can kind of see it a little bit better. That one's not so bad. And then there will very likely, if it's larger enough, there's going to be other terms, and they're not as they're not as informative, I guess we'll say. But there's always an alternating sign because of what I kind of talked about here. This actually will always be here, and that's the part I don't really want to get into because it takes a while to show that. And this we actually already just showed. This stuff isn't necessarily informative too. So that is P of lambda in one form. But P of lambda is also, right, -1 to the n, and then lambda minus lambda 1, lambda minus lambda 2, all the way up to lambda minus lambda n, right? And so what you can do, if you want to figure out, if you want to try to show that the trace of A is equal to the sum of the eigenvalues, then what you basically can do is you can just equate coefficients here. And so here we're just going to equate coefficients between these two different forms of the characteristic polynomial, right? And it's kind of computationally, notationally annoying to do. It's one of those things where, again, it's way more informative to almost see it pop up nicely with a 2x2 and then pop up nicely with like a 3x3, and like you start to kind of just accept it, I guess. But it really just has to do with how we compute determinants and how when we do the cofactor expansion, we're basically multiplying on the diagonal, and it pops up because of that really at its core. But if you equate coefficients with the lambda n minus 1 term, you really would see that the trace of A here is actually going to be lambda 1 plus lambda 2 plus blah, 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 plus lambda n. And I would totally suggest you take, you can do it for two terms, like this factor and then this polynomial. And you don't need to care about the other terms in here, right? So you only need to multiply out to see how you'll get the n minus 1 coefficient. And then you'll see it pops up as the trace. And then if you do 3 factors, do the same thing, see how you can get n minus 1. It'll pop up again. So I am not going to put a box here because I don't think I proved it by any means, but put a ghost of a box. So this one, pretty solid proof, but this one is honestly just like a lot of kind of tedious, annoying algebra, and you really have to be careful with all your notation, and it's not something I'm going to test you on. So I just really wanted you to see it. So it is true and it is weird, and if you keep taking math classes, you'll talk about why some of these things actually are what they are.